Hello, my name is Joseph, and today we're going to be talking about filtration. Now, as we all know, in X-ray, the common energy we use is X-ray photons. Now, a lot of people would associate X-ray photons with, its negative effects and everything, but the benefits of it actually outweigh the negatives as we're able to, provide analysis for the human body as we X-ray them to see, what's going on inside and all the bones and everything. So filtration is basically by definition, the removal of low X-ray photons from X-ray. Now, X-ray photons, as an example provided by my professor, can be best described as a bullet wound. As you know, a bullet that remains inside the body is actually does more damage than a bullet passing through because infection and just causing damage to the tissue. So filtration basically is the removal of the low X-ray photons that stay within the body, so that way it doesn't provide too much patient dose and it doesn't cause damage to the tissues and everything. So the material commonly used for filtration is aluminum. Aluminum has an atomic number of 13, which allows X-ray photons to travel through it, but what it does is causes the removal of low X-ray photons so it doesn't pass through and it doesn't ultimately reach the body. In filtration, there are two types. There is inherent and there is added. Now, inherent filtration is basically all the filtration that happens inside the X-ray tube. Now, here's an example of an X-ray tube with all the components that are inside. There's the filaments and the anode disc and the ball bearings and everything. So, inherent is basically composed of the housing, which is this big rectangle located around the entire inner part, labeled as 2. We have the glass envelope, which is made out of glass. It's all this that comes around, labeled as 3. And 4, we have the dielectric oil, which is located between the housing and the glass envelope. And what this does, it also provides filtration, but it absorbs a lot of heat. And as we know, X-ray photons, or inside the X-ray tube, are 99% heat and actually only 1% X-ray. So, also for added, we have this skinny aluminum sheet that contributes to the half-value layer. It's very tiny once you look at it on an actual X-ray. It's between the X-ray tube and the collimator. Now here's the collimator. It's the part of the X-ray tube that has the knobs that controls the field size. And once you increase collimation, you would reduce the field size generally. And this also is a very important part of filtration. And as you can see up here, this is the negative side, and this is the positive side of the X-ray tube. Now the negative side does have more power because the electrons do have a negative charge, so it's a lot stronger on this side. So essentially you would have the patient with the thicker part of the body located on this side of the effective focal spot. Another part of filtration that's very important is compensating filtration. Now basically what this is X-ray photons require more energy to pass through meatier parts of the body, or maybe if a patient is a little overweight, you need to have more power onto the thicker side. And basically compensation filtration is used to even out the amount of X-ray photons that reach the body, or whatever part has to be penetrated fully. Now there's 3 kinds of compensation filters is what we call them. The first one would be the wedge filter, which is shaped like, I would say, a doorstop, shaped just like this. And basically all of these filters are made out of aluminum. Just like as I stated earlier, aluminum has an atomic number of 13, which makes it a little easier to travel through than lead, for example. So for an example of using this would be, excuse my drawing, but this would be a foot. And as we all know, this part of the foot closer to the heel has the most bones and thickness. So we would need the X-ray photons to travel easily through the filter, so it's able to provide better penetration and show a clear image on the X-ray. And on this side, since towards the phalanges or the toes, we would need more stopping power. Otherwise, it would over-penetrate the image and you wouldn't get a clear image. So the X-rays are traveling through here, and they're stopped more than they would on this side, just to even out the amount of power. Another example we would have is the wedge filter, which is basically shaped like two wedge filters put together. And these filters are used mostly on the chest area. As we know, you can imagine that the lungs would be placed on these parts because the lungs are very easily penetratable, and the chest would be located here along with where the heart would be. And as we all know, the heart and this whole area requires less stopping power because it's really it needs the power to really penetrate through. And the last one would be the Furlick filter, which looks similar to the trough filter, but it is larger, and basically this is used for more like the head areas. And all of these are made out of aluminum in order to be able to pass through to still provide enough filtration to get through. Now here I have an example of what a wedge filter might look like. It is made out of aluminum, like I said, and here's the foot that I tried to draw. So basically it will be placed just like this, and you can better see how the X-ray photons would travel easily through the thinner side, but it would be a lot harder to travel through this side because, as you can see better here, the toes, they don't require that much penetration like the heel would. And that's it. Aluminum, as we know, is a good effective way to filtrate X-ray photons that reach the body. Now here we have a table showing the recommended minimum total filtration levels. Now, as we know, kVp is basically the penetrating power that you need to penetrate through thicker parts of the body, but this also applies to aluminum. So the thicker the aluminum, the more kVp you would need. So as we see on the table, under operating kVp, we have below 50 kVp, which isn't that much, but it is required to penetrate through 0.5 millimeters of aluminum, which is very thin. On the second line, we have 50 to 70 kVp, which is a little bit stronger, but we would need that to penetrate through 1.5 millimeters of aluminum. And on the bottom row, anything above 70 kVp, we would need for 2.5 millimeters of aluminum to penetrate through. And basically, so as we discussed, filtration is a very important part of X-rays. It's basically the part of X-rays that are evening out the amount of X-ray photons that reach the body depending on thickness. Here we have the inherent filtration, which is basically all these parts are located within the X-ray tube, which consists of the housing, glass envelope, and dielectric oil. We have the added filtration, which consists of the collimator and this thin sheet here that refers to the half value layer. We also have the compensating filters that consist of three common ones, which are the wedge filter, the trough filter, and the Furlick filter. And all of these are used depending on which part of the body it needs to be analyzed. And just like I showed, the thicker the part of the body, the less filter you would need to penetrate through it. And here, just like the thickness of the body, you would need different amounts of kVp, which is the penetrating force, to get through different thickness of aluminum. And just like the body parts, the more kVp used means that it's what you need to penetrate through is thicker. And filtration is very important to reduce patient dose and is a very important part of X-ray. And thank you for your time.